There were questions on the discussion, no?
Yeah, we're starting again. Are there questions about okay, then we can.
Okay, so of course, all the problem here is how do you find collective variables? So initially, this was developed in for molecular systems where people had some chemical or physical intuition of what was going on, where was the modes, what was the important coordinate to look at, and over the last 4 or 5 years, of course, people have started to try and learn collective variables with data, which is no, but I know it's just maybe not in the okay. Okay, so now, of course, it's dimensionality reduction problem. So there are lots of work on that. So let's say the question is, okay, if you give me a sample according to my probability distribution, can I find good collective variables? And so, okay, the question is, what is a good collective variables? We have already said, okay, but it's difficult to say, okay, I want to optimize the log Sobolev constant of the orthogonal coordinates. Okay, so basically our goal was to, we said, to separate the modes. So some works have been done based on classification problems. Somehow, okay, you want Xi to be a good classifier, which tells you, okay, if I give you a microscopic state X, you tell me Xi of X, tell me in which mode it is which of course requires to already know what is a mode. Okay, and if you want something without knowing where modes are, basically you are asking for, okay, you want Xi of X to keep the main important information of X. Okay, and you can see it as, okay, if I am only given Xi of X, I can still rebuild most of X, okay, just with this information, and so you end up with this kind of criterion. Okay, and of course, maybe you don't want to reconstruct X itself, but possibly just its energy because it's what you care about. Okay, or maybe you have identified some nonlinear modification of X. So like, for instance, if when you're doing images, X would be the color value of any pixel of the picture, while phi of X would be you take some convolution, some LP norm of some convolution of some part of your image. Okay, so you have some descriptors of your state, which are not the Cartesian coordinates necessarily, but that you already know are good. I mean, take some information. In particular, okay, for instance, in molecular dynamics, the system is invariant by translation and rotations, and the Cartesian coordinates are not. Okay, so it's not a good representation of, if you take Xi of X and that Xi is not invariant by a translation and rotation, it's strange, okay? And so, okay, maybe you want to unfold that. Okay, why would you try to reconstruct the energy? In fact, apart from collective variables, it's also an interest in particular in molecular simulations, to have data-based potentials. Okay, because the potential U in molecular simulation, they should be given by quantum physics. Okay, but if you do that, I mean, you fix the nuclei. And then you should have to minimize some. You should find the density of electrons with minimizes some energy, and this is very costly, so you don't do that. So you can do classical physics where you have two body interactions, okay, which is some approximation of this quantum ground truth, and okay, but which is incapable, for instance, of doing real chemical reactions like breaking bonds between atoms or things like that. Okay, and so you can okay, so the U of X, it's not clear. You have it's a model. It's a model, and you can learn a model by having data given by experiments or by simulations, ab initio simulations at the level of quantum physics. Okay, and try to learn something which so here, and what I want to say here is that okay, if you have something which reconstructs the energy and which is differentiable, then you can construct you get the forces gradient of U, okay, and it means that if you are able to reconstruct the energy, it means that you have all the information that you want somehow. Okay, and so usually, and all the information that you want is precisely what you want for Xi. So these two problems are somehow can be solved simultaneously. If you have already trained something to learn U of X, it means that in the process you have learned important features, and so you can start from that to get reaction coordinates without starting from nothing. Okay, so it's sometimes what you take for collective for criterion for collective variables is also related to the fact that you have another problem related to that, and you just solve everything together. Just a remark: in the literature, people have looked at other criterion, which is like we want to find the slow variables. Okay, the variables which evolve slowly in the dynamics, but that's really a dynamical question, and here we are just considering sampling question. We just want to sample the Gibbs measures. There is no dynamics in this question, and so okay, I'm not going to talk about that. Okay, so I'm just going to go through some examples that people have used up to now. So I'm pretty sure that here maybe each of you individually, or obviously all of you, the sum of you is much more expert than me in all these kind of questions. So I'm not going to talk about things I have worked on, but I'm going to present examples where people have really applied this kind of data-driven dimensionality reduction problems to collective variables, and then to enhance sampling with ABF or things like that. So of course, the simplest thing you can think of in terms of reconstruction is let's be linear. Okay, so let's do a PCA, which is exactly answering this question. Okay, but then okay, so maybe I haven't discussed this formula. Okay, I'm saying that psi of x is such that what have I? Yeah. It's a function which, if I take a reconstruction functions, okay, I take the best reconstruction that I get of x, given only the information psi of x. Okay, so this is how much I can recover of x, and I take the best f, and I take the best xi. So I want xi. So of course I don't say what are the functional spaces here. Okay, so I say that I want xi which loses the less information in terms of squared distance here, in the sense that ideally there would be a function which reconstruct x up to some minimal error. Okay, and what I'm saying is that if you restrict the spaces here f and j to linear function, this is what is doing PCA, because okay, you want xi of x to be linear, so given by some matrix of low rank because n is much smaller than d. Okay, such that there exists a matrix B which reconstructs x up to this minimal error, and the solution is clearly to diagonalize the variance of mu here, and just take the and so you want to kill here, you want to suppress the directions which have the highest contribution to the variance. Okay, if you take big psi equal to 0, you have x squared. You can expand that on the eigenvalues of the variance, and you just the solution to minimize that is just to take xi to be the xi to be given by the projection of x on the eigenspaces with of the variance with the highest modes. Oui. Yes. No. No, that's the point. No, I'm going to explain it. But of course, it's a problem that, okay, it's the elephant in the room. So let's say it now. If you have a sample, you can have collective variables. But all the point of the talk was, okay, we start with the collective variables to have samples. Okay, so of course, you are not going to find magically information that you don't already have. And so here, for now, I'm saying, let's say I have a sample. What would be the best collective variable? And then at the end, you apply it to whatever sample you have at end. And okay, and then you iterate. But then that's okay. There could be separate questions, which is okay. I have a sample which is exactly what I want, and I want to extract some low-dimensional information. And this is the story I'm telling now. And now you couple it with, for instance, ABF, which is okay. I do the two simultaneously, but I'll come back to that because, of course, it's the problem with all that. Okay, now just a thing about PCA. Okay, this makes sense if X is really the problem you are interested in. If you precondition X by you do first a linear transformation such that all the coordinates of X has the same variance, which is better for sampling, but then you completely lose the initial problem of interest, and so PCA makes no sense in that case. Okay, you have completely modified you have some arbitrary variances which are just which has nothing to do with the important information which was in the real problem. Okay, so just to okay, just to remark that. So of course, this is all linear, but you can do a PCI, but applied to non-linear transformation of the state. And okay, anyway, and that's basically, so this is something that, okay, I said that I was not about to talk about works that I did, but indeed, this is something we did. Just to say that, okay, PCA may sound so old-fashioned, but with all these fancy nonlinear technologies that we have now, but in fact, it works. It works sometimes. And also, okay, so the story of this picture is it was at the beginning of the COVID pandemic. And so my colleagues in computational chemistry, they wanted to simulate a part of the virus, which is its main protease. So it's okay, some part, and of course it was the beginning of the pandemic. We didn't know the modes, if I want to say it. So we didn't know the space. We had some crystallographic information. So we had an initial condition. Okay, we knew that there was some structure which was basically what we wanted. Okay, and we wanted to sample that guy. And so we had no particular insight. At least I had absolutely no insight on the energy landscape of that guy, and my colleagues didn't have much either. From a software point of view, all this ABF and other metadynamics biasing scheme that we had was not yet interfaced with the software that we are using in my team, which is motivated by the fact that it has exactly a good approximation of U with polarization. So anyway, we wanted to use our software, which is the software of my team, but we didn't have all those fancy enhanced sampling methods. We didn't have any fancy dimension reduction schemes, but we wanted to run the thing fast because, okay, it was the pandemic, so it was right now. I mean, 2 years later, nobody would have cared. And so we did something simple. So we did something simple for the biasing. So we did something which was not adaptive biasing forced. So it was not a drift. We were doing a selection procedure, so birth and death process somehow. Okay, because it was simple to fast to implement, and we did PCA for the adaptive collective variable. Okay, so the scheme was you sample, from that you do a PCA, you get some collective variable, you resample with this collective variable, and you iterate. Okay, and so this is the picture you get. Okay, and what was nice with this selection also, it was not so difficult to bias with many reaction coordinate. Okay, so anyway, so this is the sample that we have projected on the space of the two first collective variables that we had at the end of the simulation. So after 15 iteration of PCA sample. Okay, so the blue dots here are what we have, and the red dots here is what had another team who did of DE Show Research Center. They did a simulation of this very high supercomputer simulation as we did. Okay, so it was not on the laptop of someone. It was a huge simulation for many days, as we did, and this is what they saw, and this is what we saw, at least in this two-dimensional space. So we see that the algorithm did its job, which was to spread out the sampling. Okay, at least in this dimension. Okay, so we have seen much more configuration in this sense, because they were doing like vanilla molecular simulation, so no, just real physical stuff and no bias. Okay, and so we were relatively happy with that, and I don't want to comment much about the work of my colleagues and how they interpreted all that, because so then they had many analysis, post-processing of that, and find where you have some cryptic pockets within the protease. Okay, they had a bunch of things which were of biological and pharmaceutical interest that I don't understand at all, but I understand that they were happy to, they thought, they saw things that were not seen in other situations. So they saw things of biological interest, like cryptic pockets, which are parts of the protease where you have some, if enough space for some molecule to come, that were not in other configurations that I are already seen. Okay, so that's just to say, even simpler things that can increase. And just before taking questions, even when you don't know anything about the landscape and you just want to explore randomly, not randomly, but okay, without any a priori knowledge. Yes, ouais. So here, this was run on the Janzé supercomputer, which is a supercomputer in France. It was run, so the full simulation is 2 weeks, and it's for 1 day we run 100 simulation of kinetic Langevin molecular simulation, the 100 in parallel simulation for, okay, as long as you can do in 1 day, which I think what 1 picosecond of simulation of trajectory. Okay, end of the day, the Janzé computer sends us the result, and then on the computer of the PhD guy who was running that, he does the selection biasing selection procedure, and the next day he sends to the supercomputer the new initial conditions for the new 100 run, and this for 15 days. No, that's not cheap. That's typical, but that's okay. I'm not trying to sell carpets here, but just to see the order of magnitude is, so if so we were doing 100 in parallel trajectories for, I think, 1 picosecond for each day, this for 15 days. If you put that all one after the other, which of course was not the case because we are doing 100 of them in parallel, but if you put that all in together, while we were using a polarizable force field, this was a world record. There has never been that many that time spent on a polarizable force field on a system which was I think 100,000 atoms. Okay, but it's not cheap. It's a huge. I'm just saying that okay, and again, I don't have the exact settings of those guys, but it was the same kind of huge thing for several days. Okay, so it's the same kind of mammoth simulations. But here we were biased, and there were not.
Blob on the right, a lower density.
Sorry.
This blob on the right, is that part of the same?
Yes, so the red one is not our simulation.
Yeah.
The yellow one is our. So the gradient here of color is our samples, and the red ones are the sample from the unbiased simulation for the other team. Again, it's a projection in the 2-dimensional, so possibly it doesn't exactly tell you everything about the whole sampling, and also possibly, okay. It turns out that at the end, there was some clustering algorithm to see what were the configurations, and there was one configuration here, one here, one here, one here. And somehow all this was explored, what was not used at the end. Okay, so somehow if it's easy to spread the exploration. Okay, but it's not easy to spread the exploration in places which make sense. Okay, so being spread is not saying that, okay, this is incredible, we have seen so many things. Okay, so there is a whole part here which at the end is basically garbage. I mean, okay, we haven't done anything with that after that. So, other questions on that? Okay, so here is one of the first, I think, to do something. Okay, maybe I shouldn't say that because I haven't a very clear view on the whole bibliography, but it's clear that it's some important thing here. So work of Bonatti, Rizzi, and Parinello. And so here it's okay. Just taking the picture from their paper because it's very clear. Okay. And it's just an illustration of when I said that you have maybe at least two philosophy, which is either want to classify or you want to reconstruct. And here it's really a classification problem. So it's a problem where, in fact, they have, so, okay, I don't exactly remember how they have the sample, but basically the idea is you already know where are the modes. You start 100 simulation starting in one mode, and you start 100 simulation starting in another mode. So you have a sample in each mode, and you know which come from which mode. Okay, so you have two samples, one that you know started in one mode and the other one. Okay, and from this you want to construct a collective variable. Okay, and what they say is, okay, so it's they say it's a classification problem. We want collective variable which tells us if we are from mode A or from mode B, and so we want something. Okay, and so the linear way to do that would be the linear discriminant analysis. So maybe given time, I won't go into details, but okay. So the idea is, so I have two, or maybe more. Let's say two. I have two samples. I have two different samples. And the linear discriminant analysis is what is the hyperplane which best separates the two class, in the sense that, okay, no, maybe okay, I'm a bit confused. I'll go here a bit vaguely, and that's not crucial for me. So basically, you want a linear plane which decompose your data in two parts in such a way that the variance the variance within groups, you take the sum of the variance in each group, and you want this to be small with respect to the variance between groups, in the sense that if you do the average of this and the average of this, and you look at the variance of this mean, okay, you do the sum of of the mean of the difference of the square of the mean of that guy between the mean of everybody. Okay, so you want the variance between groups to be much larger than the variance inside each group. Okay, and that's the linear discriminant analysis, and it boils down to an eigenvalue problem. Okay, and then so when you have two groups here, the reaction coordinate would be given by the projection on the orthogonal of the hyperplane, which separates your data, because then you would have you would have the value would be -1 here and 1 here, okay, and you would have something like that. Okay, so that's linear. So that's you get a linear combination of this. But the point in this paper is that they feed this linear discriminant analysis not with the Cartesian coordinate again, but with some neural network, and so which is meant to learn the good features which should be discriminate. So again, you start with Cartesian coordinate. You have this where things are not separated. You do a nonlinear transformation where you want them to be separated, and then you do this linear discriminant analysis, which is going to find this. And the loss function of this guy is exactly given by the score of the linear discriminant analysis, which is the eigenvalue, the principal of eigenvalue of your principal problem, which tells you the ratio between the variance between and the variance inside the groups. Okay, so you want these variables to give the problem where the linear discriminant is very good. The separation is very good. So if you just do that, of course, it doesn't work, because it's very easy to separate. I mean, if you just want to separate, you just put things very far, and you put all the observations very close to the other in the group. So you put a Dirac function here, a Dirac function essentially. Okay. And so if you do that, this is the best way to have a good separation with LDA. But then you don't have at all a good reaction coordinate, because somehow, okay, it's like having a potential which is like that. Okay, so indeed you have a very separate modes, but then numerically you have very large gradients, and so then you have a flat part where you cannot say anything. Okay, so it's bad. So they modify this with some penalization, regularization and penalization, where they want the typical distance between groups to be not too large, and they want the variance between groups to be not too small, and so like that they get something which should look like more what you would expect. Well, anyway, so they have with this kind of stuff, they have been able to get reaction coordinate. And I'll just do another. Sorry. Yeah. No. Yeah. Yeah. The new. Yeah. They knew the modes. They knew the states. They have a state A, state B, and they wanted to have something which describe how you go from a state A from state B. Okay, and so they could they had the configurations in both states, and they knew they were in the. I mean. Yeah. Yeah. Exactly.
They don't know the location. They just know if someone belongs to one node, like this.
Yeah, in that case, they knew. I mean, okay, I don't remember how precisely they define it, but they have a clear definition. So I think, okay, maybe the way I remember, it's something like, okay, you have an initial condition, you know that this guy is state A. You have an initial condition, you know that this guy is state B, and then you run one simulation from there, and you have a sample, and you call this is a sample in state A, and then you run another guy in state B, and you say this is a sample in state B, and anyway, this is too short to have seen transitions. So everybody here is state B. Okay. Yeah.
Dogs and cats.
Yeah, so something. So okay, you have pictures of dogs and cats, and if you try to do a linear linear discriminant analysis in Euclidean coordinates, Cartesian coordinates of the pixel of the picture, it's going to be stupid. And so you start by learning something which separates cats and dogs, where you already have labels, and then you do that. Okay, yeah. Exactly. Okay, and so now this team here, they use an autoencoder. Okay, so you have you have to play to what? Okay, what do you give? How do you feed your network? Do you give Cartesian coordinates, or do you have a good descriptors already, which, for instance, are already invariant by the symmetries of the problem? Okay, and well, I guess. And you do so a neural network where the last layer has the same dimension as here, but there is a hidden layer which is much lower. And so again, this is exactly trying to solve this reconstruction problem, but instead of having linear functions, you have functions which are parameterized by some multi-layer perceptron. So okay, and again, and here in this paper, they also do this adaptive thing, which is that give me a sample, I give you a collective variable, give me a collective variable, I give you a sample, etc. And okay, so it's in the market, but I mean it's recent and it's not completely okay. You have many techniques everywhere, and it's not completely. I mean, it's still ongoing work. But as we said, okay, you can now iterate between these two things. So of course, so now it's the problem. If you don't know anything about the landscape, you have no idea what is the important features. And so, okay, if you start in some well, which is like that, you are going to say, okay, the interesting direction is this one, but maybe there is a mode here, okay, and it's not because you have a good local description that you are going to find the path in a global landscape. But okay, on the other hand, on the idea is that somehow, okay, you can still get better descriptors, better features than, again, Cartesian coordinates, okay? For instance, and if you have them, they are the driving features of the system. So, okay, so even if you, again, if you have pictures given by pixels, or you have pictures given by some global global parameters which are important, okay, more important than the local pictures, you are in better shape. Okay, you can hope that it's still going to give you information about places that you haven't seen yet. Okay, maybe you haven't seen there, but maybe it's also a question about dogs and cats, and okay, it's not about the pixel of number 22. Okay, so that's the philosophy, but okay, it can fail in general. Okay, it's not completely clear in general. Just a small comment. Okay, if you don't unbias when you try to learn the collective variable, if you don't take into account that the sample is biased, okay, you can have a problem of oscillation, which is that first you give me an unbiased problem, non-biased sample. Okay, I learned that the important direction is this one. Okay, now I do the ABF, which completely kills the metastability in this direction. And so I have a new sample, and now maybe the important metastable direction is something else. And so maybe I completely change my collective variable, but then I completely forget that okay, but initially my I mean, okay, so, I had the metastability in some part of in some direction, and so I'm going to recreate this metastability. Okay, so I have to keep, I have to be consistent along iterations on the. So I have to reweight the measure to kill the bias, to be consistent from one step to another, because otherwise I'm going to go back two steps I had already seen, etc. Well, anyway, at least that's and in particular that they observed that in this work. Okay, and my point, and the reason why I said that maybe it's time to try, as Chopin, Lelièvre, and Stolz, to do something else than molecular simulation is, okay, now, since we have these, we don't need physical intuition or chemical intuition to do this ABF stuff. And okay, so people have done that in molecular dynamics. They have considered molecular systems and they said, okay, now we can do unsupervised or midly supervised collective variables, okay? But now we can do non-physical, complete things where we have absolutely no intuition, just with that. And so, because just a word about maybe the Chopin, Lelièvre, Stolz. So what they were having, it's a Bayesian problem of mixtures where okay, so you have a parameter which is distributing according to some gamma law with some parameter. And then you have some weights which are distributing according to Dirichlet distribution. And then you have, so this is the weight of each class of the mixtures. And then they have in X class. Okay, so in class K, you take observations which are distributed according to some mu K sigma K square, where sigma K square is gamma distribution with parameters some alpha and beta. Okay, so so they have this Bayesian app. So you have parameters here with some prior distribution, and then you have observations distributed according to that. And so the point is, so alpha, FG are fixed hyperparameters, but beta here, so which is the parameter of the variance of the observations in some class, it is the random, so it's one of the parameters that you want to for which you want to sample. And okay, and so so the parameters are Q1 QK, mu1 mu K, sigma yes, sigma 1 sigma K, and or maybe there were yes, I think, and beta. Yeah, that's it. Okay, and now you have to construct collective variables, and so that okay, they didn't have any they didn't have chemical intuitions on that. So they tried several things. So they tried Q1, which so okay, they tried mu1. They tried what did they try? So they tried beta, and they tried the energy, which is like, so theta is distributed according to exponential minus beta v theta. This is the log of it is the log density of the log likelihood of that. And they also tried psi to be the energy, so the log likelihood. Which is like what you have in Wang-Landau algorithm. So just to say, they tried a bunch of things, and they observed that some things made sense. Okay, the better was beta, and somehow the reason is that, okay, first they had some, okay, beta is related to the variance that you observe. So you can have, just looking at your sample, you can infer what should be the range of beta over which you bias, which is a problem in general for which is a problem for this guy. But for beta, they had a reasonable idea of which range to bias. And then when beta takes large values, you have mixtures of Gaussians, but with high variance, which basically covers the whole sample. And so you could have mode switching and things like that. Okay, but it was like the interpretation after they tried all that okay, some things work better. But okay, it was not clear. Okay, it was not clear what to use, and I don't know what why I started to say that, but anyway, okay, now we can take the same problem. Okay, say I'm just going to machine learn some collective variable and apply the things, and okay, now we can do that. And 10 years ago, it was not as easy. And I think maybe this is one of the reasons why this method, this paper stayed somehow alone in stats literature. But okay, maybe it's because everybody was busy doing other interesting algorithms, maybe. Okay, I don't know if I have much time. I'm supposed to finish at already half an hour before. Okay, so maybe I'll stop here. Just okay. Okay now? Okay. Last remark, and and then okay. I said I would not have 3 hours, but last remark. Okay, now we can learn collective variables, so we can learn a lot of them. So we have a new problem, which is we have too many collective variables, and so we cannot keep the free energy in a grid. Okay, and we cannot, and it's not a good idea to sample the uniform distribution. Okay, the uniform distribution is good in dimension 1, 2. In dimension 10, okay, it's already you're already trying to go outside the canyon maybe, and so it's not good, and so you have questions about that. Of course, you can have many ideas when you have more than one drift, one collective variable. You can treat each one individually. You can exchange like in temperature exchange algorithms, and you can do tensor approximations, which is what we did with Tony and Virginia Erlacher. And this is the last one. Instead of sampling the free energy, you can just try to explore it, just to find the modes. Okay, we forget the samples, so forget to be statistically relevant. You just want to find the modes, and you can find free energy saddle points, and then you can switch between gradient descent, Langevin dynamics, and noisy saddle point, and just to try and find the modes. And then just to say that when you have the modes, you are going to be able to use many other techniques. Interesting, and so that's for me. It's the important for me. The best thing is not to start by doing enhanced sampling. It's start to find the modes, and then you can do more interesting things. And so that's a picture that we did with in a work that we did with Lucas Journel with a PhD of mine, but it was not the free energy, it was just a low dimension within the energy. Well, anyway, so this is the kind of thing that could be of interest, and I guess the slides will be available somewhere, so you have all the references of things I have mentioned. Sorry for being so long. Thank you for your attention up to now. Yes. Yeah.
Much smaller than hand, and might be stuck in substance.
So the bias tends to repel you from where you've already been, because okay, if you've been somewhere for long, it means that you have a potential well, and so it means that you are going to learn the free energy here, and so the free energy is going to push you away. So it's not something which gets you stuck; it's something which repels you in the space of collective variables. But now the problem is the picture is erased, where by trying to do something in some direction, you destroy something which was nice, and then you may possibly, by trying to, and that's a bit something I said when I said you can have bad collective variables, where it brings you in some part of the space and you don't know how to, you never leave it indeed, because okay, you're in something which completely unphysical, and you are not going. You have new metastability, but it's even worse because you are stuck in a region which is not even of interest. And that can happen. But again, that's a question of how you choose your collective variable. Yeah, but it's only based on your sample. So if you don't have a good sample, you cannot understand that you have a bad sample. But I think, okay, there could be a sanity check for that, where you can check I mean, you know your real distribution. So if you see that the energy is very large of where you are with respect to where you were at the beginning, you know that something is wrong at some point. Okay, but